Hello everyone, this is Team 6. We're going to present our project under the title of Predicting Potential Trips for Bixi Stations in Montreal. Bixi is a public bicycle sharing system launched in Montreal in 2009 and has become a transportation option with thousands of users increasing yearly. In 2021, the number of trips increased by 22% from the previous year, encouraging the company to increase its number of bicycles and stations. As the usage of Bixi bikes grows each year, the shortage of available bikes in certain stations has become a prominent issue. This can lead to frustrated users and a reduction in service usage, causing inconvenience for users who may struggle to find a bike at one location. One possible solution to this challenge is to leverage machine learning technology by developing a predictive model that can forecast the likelihood of bike shortage at specific stations during certain periods. Bixi can take proactive steps to redistribute bikes and ensure a more balanced distribution across all stations.
This is a cost-effective transportation option that provides biking services to citizens by eliminating the need to own or maintain a bike. Apart from promoting physical activity, Bixi also helps reduce the carbon footprint and improve air quality. But to encourage citizens to use Bixi more as a convenient and sustainable means of transport, it is crucial to address the issue mentioned in the problem statement. In this regard, our objectives are focused on predicting bike-sharing demand. By analyzing our data, we can find the attributes that have the highest correlation with the number of trips. We will then narrow down the most popular regions using clustering technique. With this data, we can evaluate different algorithms to find the one with the highest accuracy. By doing so, we can finally predict the potential trip and using this prediction to allocate the resources to level the demand.
We'll use Pearson correlation coefficient to identify the attributes with the greatest impact on bike trips. This measure evaluates the linear relationship strength and direction between each attribute and the target attribute. By focusing on the most influential attributes, we can identify patterns and trends that contribute to higher trip numbers. With DBScan, an unsupervised clustering method, we'll focus on the busiest Bixi stations in Montreal. With over millions of annual bike trips across 600 plus stations, DBScan is ideal for complex datasets with varying densities and noise. This will help us identify the busiest areas of Bixi stations.
Based on the empirical models and since our goal indicates predicting number of potential trips, we decided to analyze our datasets with random forest and k-nearest neighbor regression. Both of these algorithms are often used for predicting numerical values. In addition, random forest and KNNR are non-parametric algorithms, meaning that they don't make assumptions about the functional form of the relationship between the predictors and the outcome, making them well-suited for modeling bike-sharing demand since it is likely to have a non-linear relationship with its predictors. At last, both random forest and KNNR are robust algorithms. While KNNR is robust to outliers in the data, random forest can handle noisy data and can generalize well to new data. For evaluation of our algorithms, we are going to use R-squared and mean squared error to evaluate our KNNR model. MSE is a widely used metric for evaluating regression models. It measures the average square difference between the predicted and actual values. In the next step, we are going to use R-squared method to see how well the regression model fits the data. R-squared measures the proportion of variance in the target variable explained by the independent ones. Also, we chose cross-validation to evaluate our final random forest model. It splits the dataset into training and testing sets for multiple times and averages the performance over the different splits, and we will try to reduce the risk of overfitting by cross-validation.
The data warehouse built for this project contains data from three datasets. The first dataset is a travel history given from the official site of Bixi. We have considered 2 years of data, 2019 and 2020, which contains data points like start and end date of travels, capacity of each station, and so on. For the early data analysis, we prepared a few charts. This map shows approximate location of Bixi stations and was generated by giving the attributes of latitude, longitude, and also station ID of each station to the MapDiff site. These two bar charts, generated by RapidMiner from travel history datasets, show number of trips in the months between March to September. It is clearly seen that the total trips increased significantly in 2022 in comparison with 2019, which leads to more demand for Bixi bike sharing. The second main dataset, taken from Montreal Weather State site, contains wind speed, temperature, relative humidity, and wind chill. Here the graph of temperature of each month in Montreal is presented. Considering this graph, we can find different temperature periods which can affect Bixi demand. The third dataset contains information about events in a specific area of Montreal, which can has a major effect on Bixi demand as well. Our remaining steps include apply different machine learning regression models like random forest and KNNR, and evaluating the performance of prediction of potential trips and selecting the most accurate one.